All right, let others also join. Then we'll start in about few minutes when others joins. Okay, let us start. So welcome everyone. The week 8 tutorial of thermodynamics. So in the previous tutorial, we have done a lot of good questions, and in continuation to that, we'll be doing more questions in detail in today's tutorial as well, so that you all have a good practice for solving the numerical. Okay, let me share my screen. I hope my screen is visible. All right. Okay, I'm visible as well. All right, let us start. Question is like this. 0.5 kg executes a Carnot cycle having efficiency of 50%. Okay. Then heat transfer to air during isothermal expansion is 40 kilojoules. At beginning of isothermal expansion, pressure is 7 bar and volume is 0.12 meter cube. You need to determine maximum and minimum temperature of gas in Kelvin, volume at end of isothermal expansion, isothermal expansion in meter cube, and also work transfer and heat for each of 4 processes in kilojoules. You can take for air Cp and Cv values as 1.008 and Cv as 0.721 kilojoule per kg Kelvin. Okay, all right. Do this. Pretty good question. Take some time and think about it. It's a very basic question on Carnot engine. Okay. All right, I guess few of you have done. Let us start discussing now. Okay. So there is a 0.5 kg of idle gas, and there is a Carnot engine. Carnot cycle is there, which has an efficiency of 50%, and there's a heat transfer during the isothermal expansion, 40 kilojoules. The pressure is given, volume is given at the beginning of isothermal expansion, and we need to determine maximum minimum temperatures, volume at the end of the isothermal expansion, work transfer and heat transfer for each of these four processes. Let us start. So first of all, we will make a TS plot, temperature entropy plot for that same. This is temperature, this is entropy. Okay. So we very well know that it looks like this. We have already discussed in detail all these plots. So this is process 1, 2, 3, 4. Okay. Okay. So process 1 to 2 is isentropic or isentropic compression. Okay. 2 to 3 is isothermal expansion, 3 to 4 is isentropic expansion, 4 to 1 is isothermal compression. Okay. Right. So, and the efficiency of the engine is given as 50%. So efficiency is nothing but 1 minus. So let us assume this is T higher, which is required, and this is T lower. We don't know what is T higher and T lower. Okay. And that is given to be 0.5. 0.5. So we know the ratio of T higher to T lower is nothing but 0.5 only. Okay. 0.5. Now let's go process by process. For process 1 to 2. So process 1 to 2 is nothing but PV raised to power gamma is equal to constant. So it's an isentropic compression. We know that during the isentropic, it's adiabatic as well, adiabatic reversible. So there is no heat transfer. Okay, so Q1 to 2 is 0. Okay, since isentropic, right? Then work for an isentropic process, we know that what is the work net? So it is P1 V1 from 1 to 2 you are going P1 V1 minus P2 V2. So it's a compression, isothermal expansion, sorry. Sorry, 1 to 2 we are going isentropic compression. So whenever there is a compression, the engine will take the work supply. Okay, so work is given currently during the compression process. So it should come out to be negative value, right? It said work has been absorbed. P1 V1 minus P2 V2 over gamma minus 1. And for idle gas, we know that PV is equal to MRT. So MR T1 minus T2 by gamma minus 1. All right. Is it clear? So we don't know what is T1, T lower and T higher. T1 is T lower and T2 is T higher. Okay, from the graphs. For that, we need to have the values. So we can get, we know that since P2 V2 MRT2 from the idle gas, all right, it's given the pressure is 7 bar at the beginning of isothermal expansion. Okay, so 7 bars, that means 7 into 10 to the power of 5. Volume is also given to be 0.12. Mass is given as 0.5 kg in the question. R for the air is 0.87 to 10 to the power of 3 kilojoule per, and converting to joules. And T2 you don't know. All right. So what is T2 from here? If you solve, T2 comes out to be 585 Kelvin. 585 Kelvin. That is nothing but your T higher. So you got T2 and T higher. All right. Also, you know that since T lower but T higher is nothing but 0.5. So you can say that T lower will be 0.5 times T higher. That is, if you put the value 0.5 into 585, so T lower comes out to be 292.5 kelvins. And that is nothing but equal to your T1. Okay, that is T lower. You got both the values. Put these values here, T1 and T2. So let us name that this equation 1. Put T1 and T2 in equation 1. T1 and T2 in equation number 1. All right. So what is equation number 1? Work from 1 to 2 is nothing but MR. And what is M and R? Let us put that. M is 0.5, R is 0.287. We'll keep it in kilojoule only because we want the work and heat transfer processes to be in kilojoule as demanded in the question. T lower is 292.5 and T higher is 585 by gamma minus 1. Gamma is 1.4 minus 1. So it comes out to be negative of 104.8 something. So that is 105 kilojoule. Eventually it should be a negative value. So it's a compression process. So work net is work from 1 to 2 is negative of 105. All right. Okay. It's also said that heat is supplied at 40 kilojoule during isothermal expansion. So here heat is supplied. Oh. So heat has been supplied of 40 kilojoule. You don't know what is heat rejected. All right. We don't know what is heat rejected. Okay. Now from 2 to 3, again come to the process number 2 to 3. So you got work transfer, heat transfer, T lower, T higher. Okay. What is process 2 to 3? So process 2 to 3 is isothermal expansion. So whenever there is an isothermal expansion, that is T is equal to constant. That means net work is net heat. Okay, we have discussed this very detailed because it's a rectangular hyperbola, the graph of PV. Okay, so net work is net heat. So Q net is nothing but equal to work net. But what is work net? That we need to find out. So how you will get the work net? So work net will come out to be from 1 to 2. So I'm 2 to 3. Okay. From for the process 2 to 3, how you'll get the work net? That's the challenge. You tell me. Anyone of you have done? Am I audible? So anyone has typed? Just hold on, please. Yeah, sorry for the interruption. Yeah, so I was saying what is work net? So just now I said that for a constant temperature, heat is equal to work net, and heat in the 2 to 3 is given to you in the question itself. I just made. Okay, so that is 40 kilojoule. Therefore, since Q1, 2 to 3 is 40 kilojoules, given. Therefore, work 2 to 3 is also 40 kilojoules. Okay, so you got the work net and Q net, Q 2 to 3 and work 2 to 3. Now let's come to the next process, 3 to 4. So process 3 to 4 is isentropic expansion. Again, PV raised to gamma constant. Okay, so isentropic expansion again, heat is Q3 to 4 will be 0 since isentropic, reversible, adiabatic. Okay, and what is work 3 to 4? It will be same as work 1 to 2, just it's an expansion, so it will be just a with a positive sign even if you put the values. So even if you put the values T3 minus T4 by gamma minus 1, if you put the values, so it is 0.5 into 0.287. So what is T3? 585 minus 292.5 by 1.4 minus 1. Same value, just with a positive sign it's going to come. So work 3 to 4 is 105 kilojoules. And here heat was this. Okay. Now next process is 4 to 1. Process 4 to 1. So process 4 to 1 is again isothermal compression. So again temperature is constant here. So again heat from 4 to 1 is equal to work from 4 to 1. Now what is work from 4 to 1? That we need to find out. Okay. That is, or what is heat we get out of that. So we know that since efficiency is 0.5 and that is nothing but equal to work net of the cycle to that of Q supplied, and work net is Q rejected minus Q supplied by Q supplied. So that is 0.5, 1 minus, am I being wrong? Q supplied minus Q rejected. 1 minus Q rejected by Q supplied. So Q rejected by Q supplied is 0.5. And you know that what is Q supplied? Supplied is in 2 to 3 process. So QR is 0.5 into Q from 2 to 3 process. That is given to be as 40. So Q rejected is 20 kilojoules. Okay, that will come out with a negative sign. It's a either you write Q interaction or rejection. So Q rejected is nothing but Q process 4 to 1. Okay, so that you got. Since Q4 to 1 is this, therefore work 4 to 1 is also equal to Q4 to 1, that is 20 kilojoules. 20 kilojoules. It's a negative value. Okay. Now we got all the heat transfer values, all the work transfer values for all the processes. We got the higher temperature, we got the lower temperature. We need to find out volume at the end of isothermal expansion. That is volume of V3 we need to find out. Okay, isothermal expansion V3 we need to find out. Let's find out. So since work from 2 to 3 is an isothermal process. So for an isothermal process, we know the formula. Right now we were just saying that it's isothermal process, work transfer is equal to heat transfer. We directly wrote. But what was the expression for the isothermal process? So that was MC ln V3 by V2. Okay. Or you can say P2 V2. MC is nothing but ln V3 by V2. We have done this. So we know that what is 2 to 3, 40 kilojoules we got. What is pressure at the beginning of isothermal expansion? That is 7 bar. 10 to the power of 5. What is volume at the beginning of the expansion? That is 0.12 ln of V3 you don't know, but you know 0.12. So let us solve this, and what value we'll get out of it is, let me see, 40 divided by 7 divided by 5, 10 to the power of 5 divided by 0.12, exponential of this into 0.12. So we got point some got out. V3 comes out to be 0.193 meter cubes. Okay, so that was the value required. Okay, so I'll explain once again the whole process. Sorry. So there's a Carnot cycle. Okay, from 1 to 2, 2 to 3, 3 to 4, 4 to 1. Efficiency of the Carnot cycle is given to be 50%. Uh, heat supplied is given from 2 to 3 process is 40 kilojoule. That is your isothermal expansion process. You also know that what is pressure at 2 starting of isothermal expansion, that is 7 bar, as well as volume as 0.12 meter cubes. Okay, you need to find out what is the heat interaction in each of the process, that is Q rejected, also need to find out, as well as the work interaction in each of the processes, as well as lower and higher temperatures. So what we have done, we know the Carnot efficiency is 0.5, so we know the T higher to lower as 0.5. For process 1 to 2, that is isentropic compression, it's an isentropic, that's why heat reversible adiabatic, so heat interaction will be 0. And we know the expression for work interaction, that is P1 V1 minus P2 V2 by gamma minus 1, or MRT1 minus T2 by gamma minus 1, because PV is equal to MRT. So but we don't know what is T1 and T2 so far. So first of all, we will get the T2 from the expression P2 V2 is equal to MRT2, because you know P2, you know V2, you know M, you know R, you get the T2 as, that is your T higher, as 585. So 585 you get as your T higher. So also from this ratio T lower to T higher is 0.5, you get the T lower as 292.5, that is your T1. Put this T1 and T2 in the equation number 1. You get the work 1 to 2, that is negative of 105, because it's the compression process. Work is absorbed by the system. Next is process 2 to 3. So 2 to 3 is the isothermal expansion. So temperature will remain constant. And you know that for isothermal process, net heat interaction is net work interaction. It's a rectangular hyperbola, the PV plot, if you see, if you have read in the previous tutorial. So we know that heat supplied from 2 to 3 is 40 kilojoules given in the question. So that is nothing but your work net as well. 40 kilojoules from 2 to 3. Now coming to the 3 to 4 process, it's an isentropic expansion process. Again, it's an isentropic reversible adiabatic. So heat interaction will be 0. Work interaction will be, again, put the expression MRT3 minus T4 by gamma minus 1. This time it's just the same value gonna come with a positive sign because it's an expansion process. So 105 kilojoules. Now process 4 to 1 is again an isothermal compression, temperature is constant, so net work interaction is net heat interaction. But this time we don't know what is heat rejected or Q4 to 1. We know that efficiency is 0.5, that is work net by Q supplied. Work net is Q supplied minus Q rejected by Q supplied. So you can write Q rejected by Q supplied as 0.5, okay, as 0.5. So Q supplied 2 to 3 is given to you 40 kilojoules. Multiply by 0.5, you get Q rejected as 20 kilojoules. And that is nothing but your work in it as well. Okay, 20 kilojoules work in the compression process, isothermal compression process. Now we need to find out the volume. So work 2 to 3, we know that it can be written as P2V2 ln V3 by V2 or MC ln V3 by V2, whatever value you want to put. So you get the V3 from here, you know the V2, 0.193 meter cube. A very good detailed question, you understand. Now let's come to the next question. Okay. A household refrigerator is maintained at temperature 2 degrees Celsius every time door is opened, introducing average Average of 420 kilojoules. Okay. But making small changes in temperature. Change in temperature of refrigerator. Door is opened 20 times a day. And refrigerator operates at 15% of ideal COP, coefficient of performance. We have seen this. Laplace and Kelvin statements. Okay. Cost of electricity is rupees 2.5 kilowatt per hour. And atmospheric temperature is 30 degrees Celsius. Then determine monthly bill for this refrigerator in rupees. Okay. Do this question, please. Okay, let's start discussing. Yeah, so there is a household refrigerator which you have at your home household, and it's operating between a temperature limit of 2 degree and 30 degree. Okay, your refrigerator is maintained at 2 degree and our ambient temperature is 30 degree given to you. And it said that 420 kilojoule of heat is added whenever you open the door, and 20 times a day you open the door. So you know what is the total amount of heat you add. Okay, and the refrigerator operates at 15% of the ideal coefficient of performance. Okay, so it's not ideal refrigerator, it's household refrigerator. And cost of electricity, you know that it's 2.5 rupees per unit. That is kilowatt per hour is the unit for that. You need to find out the monthly bill. Okay, this question is very interesting for all of you because from now onwards you will be able to calculate your monthly bills. All right, let's come to the solution. So let's make a simple cycle. We have a refrigerator operating between two temperature limits. That is, higher temperature is at 30 degrees Celsius, and so it's 303 Kelvin. 303 Kelvin, and lower is 275 Kelvin. Okay. Eventually, it's a refrigerator, so heat will be supplied to it. That is Q1. Work it will absorb, and heat it will reject to the ambient. Okay, you don't know what is, let us say it's Q2 instead QR. Okay, so what is the amount of heat is given? So since heat supplied is equal to 20 times, one time the door opens is 420 kilojoules, so it's 20 times in a day is equal to 8400 kilojoules of heat is supply, and that is nothing but your Q1. Okay, in a day, 8400 kilojoules per day. Okay, per day of heat is supplied. Okay. Now it is also said that COP of your refrigerator is 0.15 times of COP of your idle refrigerator. Okay, what is the coefficient of performance in a refrigeration? You want a lower temperature and a you can say, so it is, you want to maintain at a lower temperature, that is T lower by T higher minus T lower in case of idle. Okay, so and in case of real refrigerator, it is whatever heat you want to extract out, that is Q1, and whatever is the work net, whatever is the work net. All right, so what is T lower given to us? That is 275. What is T higher? It is 303 minus 275. Okay, and what is this value coming out to be? Let's calculate. So 303 minus 275 was into 275 into 0.15. It's Q1 by work net is 1.473, and work net will come out to be, what is Q1 8400 by 1.473 was to 8400. So that is 5701.81 kilojoule per day of work is absorbed by the refrigerator. Okay, kilojoule per day of the work is absorbed. Okay, by the refrigerator. It's in one day, so in 30 days it will be, so work net is equal to 5701.81 into 30. That will be kilojoule per month. Okay, into 30, that is 171054. 171054.54 kilojoule per month. Okay, that is your monthly heat absorption. For a day it was 5701, and for a month it's 171054. Now, it is said that it is rupees 2.5 kilowatt per hour is the cost. So since cost of electricity, so it's for a month and it's for a day. Okay, day and month. Cost of electricity is given to be rupees 2.5 kilowatt per hour. Okay, so can you convert this? 2.5 kilowatt is kilojoule per second, and 1 hour has how many seconds? 3600. So if you multiply by 3600 in denominator, so it is, got it, kilojoule per second. Am I right? Okay. So it's rupees per kilojoule. So it comes out to be 2.3600 divided by 2.5. It's nothing but 1 by 1440. Okay. Kilowatt is kilojoule per second. Okay. And what is R in second? That is 3600. Okay. I'm going right. So it's rupees 1 by 1140 kilojoule or kilowatt per second. Okay, I should try it like this. And R is converted into second. So it's 1 by kilowatt per second. Okay, kilowatt per second. That is your cost of in kilowatt per second. Your is in kilojoule per month for a monthly basis, and this is in per second basis. Okay, per second basis. So if you multiply this with so work net into cost is nothing but 171054.54 into 1 by 1440. And if you balance out the units, that is kilojoule per month, and it is rupees is also there, rupees kilowatt per second. Are we going right? Okay, if you do the calculation, what it should come? It should come out to be rupees 118. Okay, let us see. Hours into 171054.54, 118.78. So monthly bill comes out to be rupees 118.78. Okay. All right. Any doubts? It's clear, I guess. Okay. So I can remove this, just write in the form of rupees and just multiply. Okay, pretty simple question. So we know what is heat supplied per day. That is 20 times it's open. COP of idle is actual is 0.15 time of idle. So we know what are lower and high temperature limits. We get Q1 by work net, and from there we get a work net that is per day. For per month, you multiply by 30, and you know cost of electricity and 2.5 kilowatt per hour. So in convert in second, so work net comes out to be into cost comes out to be a monthly bill. That is rupees 118.7. Okay, now let's proceed to the next question. At the beginning of compression stroke of two-cylinder internal combustion engine, AC engine, air at pressure of 101.325 kilopascals. Compression reduces volume. Reduces volume to 1/5 of original volume. Law of compression is given as PV raised to the power of 1.2 is equal to constant if bore and stroke of each cylinder is 0.15 meter and 0.25 meter. Determine power absorbed by compression stroke in kilowatt. If engine speed is such that each cylinder undergoes 500 compression stroke per minute. All right, do this please. Okay, let us start discussing. So it's given in the question that again it's a two-cylinder IC engine this time, and air is at a pressure of 101.325 kilopascals. During the compression, the volume reduces to 1 by 5 of its original volume. Okay. Bore and stroke means diameter and the length of the stroke one position to another position is diameter is 0.15 and length is 0.25 to complete that stroke. You need to find out the power absorbed in the compression stroke in kilowatt if it is said that engine is undergoing 500 compression strokes per minute. Okay. All right. So let's do. So it's given that initially pressure is given out to be 101.325 kilopascal. Okay. Also it's given that V2 is V1 by 5 from compression. So if you suppose this is a engine, two-stroke engine, suppose. Okay. So from position 1 to position 2. Okay. So this is position number 1. This is position number 2. Okay. This is a piston cylinder kind of device. And it is given that the diameter, that is bore, is around 0.15 and length is 0.25. So this is 0.15 and this is around 0.25 meters. So length of the stroke. Okay. So 1 to 2 position. Also it said that the gas behave as PV raised to power 1.2 is equal to constant. Okay. Diameter is 0.15 meter and length is 0.25 meter. Okay. Now we know that for a polytropic process, what is the expression for work done? So work is nothing but P1 V1 minus P2 V2 by n minus 1. And this is in will be done 2 times because from 1 to 2 and 2 to 1. Okay. 1 to 2 and 2 to 1. It will be 2 times for in that scenario. But if you don't want 2 times, then it will be only for the compression stroke. It will be only 1 time. Okay. Now, from the expression P1 V1, so P1 V1 to the power of 1.2 is equal to P2 V2 to the power of 1.2. Okay, that's given to us. So what is P1? 101.1325 into what is V1 you don't know to the power of 1.2. P2 you don't know, V2 you don't know, but you know the ratio of V1 by V2. So P2 comes out to be 101.325 into V1 by V2 to the power of 1.2. Since V1 by V2 is 5, okay, because final volume is 1/5. Okay, so V1 by V2 is 5. Put this value here. So that comes out to be 101.325 into 5 to the power of 1.2. So from here, P2 comes out to be 699 kilopascals. 699 kilopascals. Okay, this is your P2 because you don't know these values P1, V1, P2, V2, how you'll get the value of the work. So you know one P1, you know V2, you don't know V1, V2, you just know the ratio. Also, since we know that V1 minus V2 is the volume swept by the piston in the cylindrical piston cylinder device. So that is pi by 4 d square L is the volume of a cylinder. So V1 minus V2 is pi by 4. What is diameter? It is 0.15 square. And what is length? 0.25. Okay. So from here it comes out to 4.41 into 10 to the power of minus 3 meter cube. Okay, that is the swept volume. And you know that V2 is V1 by 5. So that is 4 V1 by 5 is equal to 4.41 into 10 to the power of minus 3. So from here you get the V1 coming out to be 5.5 into 10 to the power of minus 3. Okay, let's calculate as well. So 4.41 into 5 divided by 4, 5.51. Okay, so V2 will be 1/5, 1.1025 into 10 to the power of minus 3 meter cube, meter cube. Put these values in back in the work. So since, so I was saying here it will be multiplied with 2. Since, and let us say that this expression is 1. Put values in equation 1. So work net comes out to be from process P1 V1 minus P2 V2 by n minus 1 times 2. So what is P1? It is 101.325. What is V1? 5.5. 1 into 10 to the power of minus 3 minus what is P2? 699. What is V1? 1.1025. 10 to the power of minus 3 divided by n is 1.2 minus 1 to the power of 2 the multiplied with 2. Okay, and it is said that it is 500 revolutions per minute. So what is per second? Because you want, it is in kilojoule, but you want the answer in kilowatt. So you'll multiply with kilo, you should have kilojoule per second. So 500 revolution per second is 500 by 60. Okay, so right here 500 by 60. So final work come out to be minus 17.7 kilowatts. Okay, this is your final expression. Okay, pretty simple question. So there's a two-stroke engine from 1 to 2. Diameter is 0.15, length is 0.25. The gas is behaving as PV raised to power 1.2 is equal to constant. Initial pressure P1 is given to you. Final volume is 1/5 of the initial volume. You know that work for a polytropic process is P1 V1 minus P2 V2 by n minus 1, and only 2 times for the two strokes are happening altogether. Okay, so put the value, but you don't know the values of P1 V1 P2 V2 explicitly. So P1 is known 101.325. P1 you don't know, V2 you don't know, and but the ratio of that you know, that is coming out to be 5. So from here you get the P2 value. Put this P2 value. Now you don't know what is V1 V2 explicitly, so you know that V1 swept volume is pi by 4 d square L for that engine. So you know the d, you know the L, the values, and V2 is V1 by 5. From here you get the V1, that is 5.51 10 to the power of minus 3 meter cube, and V2 is V1 by 5, that is 1.1025 10 to the power of minus 3 meter cube. Put all these values in the equation 1, and it's given as 500 revolutions per minute. So 500 revolution per second will be divided by 60. You will get the net work as kilojoule per second this time, that is kilowatt, 17.7 kilowatts. Okay, now let's come to the next question. Air is contained in piston cylinder. Assembly with cross-sectional area of piston is, that's 4 centimeter square. Okay, initial volume of air is 20 centimeter cube. Air is initially at 1 atmosphere. pressure and 20 degrees Celsius. Spring is connected to piston cylinder assembly, which is initially under dam, which is initially undeformed position and having spring constant as 100 Newton per centimeter. Then how much heat must be supplied to air to increase pressure to 3 atmosphere, and apparatus is surrounded by atmospheric air. All right, do this question please. Okay, let us discuss, I guess. A simple question. So again, it's a question which states that air is contained in a piston cylinder kind of device. Okay, with the cross-section area of piston is given to you. Okay. Yeah, cool. And it's given that initial volume of the air is given. Air is initially at temperature pressure condition is given. Okay, and it is connected to a spring. Okay, piston cylinder device, and it's asked at how much heat we should supply that the pressure increase to 3 atmosphere. All right, so let us do. So first piston cylinder, so in state 1 to state 2. Okay, we have scenario like this. So initially the piston is supposed like this, and finally the piston goes to this position. Let us make two different diagrams. Okay, let's make two different diagrams. Okay, so initially gas is here, and this is connected to a piston cylinder. The arrangement is attached to a spring. Okay, now this has been compressed to some state. So spring will get compressed from this state to this state. Okay. So initially it is acted upon by pressure ambient P naught. Finally, it is also acted upon by P naught. Okay. Initial pressure inside it and volume is given. P1 is 1 atmosphere and volume is given out to be 20 centimeter cube. Okay. We don't know what is final volume, but we know what is pressure. Final pressure comes out to be 3 atmosphere. Eventually, there's gonna be a spring pressure force by the spring. So we say the pressure is PS. Okay, from state 1 to state 2. All right, and it's given the spring constant K is given out to be. This is some K of a spring that is 100 Newton per centimeter. So we know that since P2 is equal to P naught, sorry, P of spring plus P naught from this state. Okay, all right. What we don't know is what is spring. So we know that it goes up to 3 atmosphere, that is 3.03. You know that it is 1.01, but you don't know what is P of the spring. Okay, you know what is final pressure, you know what is initial pressure inside. Okay, so I'm just balancing the force in this diagram. Okay, initially P1 and P naught will be same because they are balanced. PS will be 0. All right, I guess you're a bit confused here. This is your state 1. This is your state 2. Okay, so in state 1, spring is not deformed. Since spring isn't deformed, so force balance, by force balance or pressure balance, P1 is equal to P naught plus PS. So it's not deformed, so P1 is equal to P naught. In the second scenario, P2 will be P naught plus PS. Okay, that is 1 atmosphere, 1.01 or whatever. All right, so P naught, P2 is 3.03 1.01. So PS comes out to be 2.02. That is your spring pressure. You know that pressure is force upon area. So spring force is Kx. Oh, you don't know what is X displacement by the spring. So let us say, I'll write 2 here. So this is your X displacement from this to this position by the spring. Okay. Since pressure of spring is force of spring by area, right? So area, no, that is given to be 40 centimeter, 4 centimeter square. This is kx by 4 to the power of 10 to the power of minus 4 meter square. And k is given as 100. So it will be 10 to the power of 4 Newton per meter. It's Newton per centimeter. And you don't know x. PS spring, PS you know, 2.02 into 10 to the power of 5 into the power of 4 by 4 into 10 to the power of minus 4 is equal to x. So x comes out to be 8.08 into 10 to the power of minus 5 meters from here. So this much amount of displacement has been done. Minus 3 meters, sorry, 5. Okay, 0.8, almost 8 mm of displacement has been done by the spring. Since you know that final volume minus initial volume is area into displacement. So area of this and what has been displaced. Okay, so it's more of a cylinder volume A into X. So you know initial volume, you don't know final volume. Initial volume is given at 200 centimeter, I guess, or 20 centimeter, 20 centimeter cube. So it is 20 into 10 to the power of minus 6 for meter. Area is given to you 4 into 10 to the power of minus 4. And X you have calculated as 8.08 into 10 to the power of minus 3. So final volume comes out to be 23.23 into 10 to the power of minus 6 meter cube. So you have initial volume, you have final volume. Okay. So it's a linear variation if you observe for a spring mass system. If I draw a plot like this for a pressure volume plot. Okay. So initial pressure, you know that it is 1.01. Final pressure, you know that it is 3.03. So I'm writing in atmospheres. Okay. Initial volume, you know that 20 into 10 to the power of minus 6 meter cube, and final volume is 23.23 into 10 to the power of minus 6. So it's a spring mass system. It's a linear behavior for a spring mass system to be. So this gives you a linear behavior like this. Now you can calculate from the area under the pressure volume plot, gives you the work done. Okay, so it's more of a trapezium. Okay, so we can calculate the work. So work net is half into sum of parallel sides into the height. Okay, so height is 23.23 minus 20 into 10 to the power of minus 6 into sum of parallel sides is 2.02 into 10 to the power of 5. Okay, all right. So work net comes out to be 0.656. Am I right? Just a second. So these are the parallel sides. Okay. So it is 1.01 plus 3.0, 4.03. I made it. I wrote 4.04 into 10 to the power of 5. Okay, cool. So this comes out to be 0.656 joules of work. But question has asked how much heat we need to supply. So we know from the equation dq is du plus dw. We know what is work net. We don't know what is du. So du can be written as mr mcv dt. Cv is r by gamma minus 1 and t2 minus t1. Work net is 0.656. This can be written as P2V2 minus P1V1 by gamma minus 1. P2V2 minus P1V1 because it's an ideal gas eventually plus 0.656. You know what is final pressure, you know what is uh, final initial volumes. So P2 is 3.03 into 10 to the power of 5. What is final volume? 23.23 into 10 to the power of minus 6. What is P1? 1.01 and 10 to the power of 5 into what is V1? 20 into 10 to the power of minus 6 by 1.4 minus 1 plus 0.656. So after solving, you will get the net heat transfer coming out to be 13.25 joules of heat you need to provide. All right. Okay. This is your final answer. Pretty simple. Okay. Any doubts in this? No doubts? Okay. All right. Let's move to another question. So, so I'll explain once again in a one go. So there is a spring piston cylinder arrangement connected to the spring. So initial pressure is 1 atmosphere, initial volume is 20 centimeter cube. You know what is ambient pressure, and there is some spring pressure eventually. Initially it is undeformed, so spring pressure will be 0. But if it is what heat is applied to the system so that the pressure is reach to 3 atmosphere, you need to find out what is the heat supplied to the system. So in the first case, spring is undeformed, so PS will be 0, P1 is equal to P 0. In the second case, P2 is equal to P 0 plus PS. Uh, P2 is 3.03, P 0 is 1.01 plus PS. So PS comes out to be 2.02, and this is spring pressure. Spring force is Kx. So pressure is force over area. PS is Fs by area. So Kx by area 4 into 10 to the power minus 4 given to you, and k is given 10 to the power 4 and x you need to find out. So from here you find out the x as 8.08 into 10 to the power of minus 3. Then what is the swept volume can be written as area times the height. That is the cylindrical volume V2 minus V1. Initial V1 you know, V2 you don't know. Put the value of AX, you get the V2 as 23.23 10 to the power minus 6. Plot it on the PV plot because it's a spring mass system, it's going to behave a linear. So PV, so initial pressure, initial volume, final volume you know. So I'll write this as initial states and final state. 1, 2. So from the area of by the if you see from the geometry, it's a trapezium. You can find out the area under graph of PV gives you the work net that is half into sum of parallel sides to the height. Okay, so work net is 0.656. You know from the equation dq is du plus dw. So du can be written as mcv dt. Cv can be written as r by gamma minus 1. And eventually it can be written as P2 V2 minus P1 V1 by gamma minus 1 plus the work net is 0.656. Put all the values of pressure, volumes, and you'll get your final answer as this much amount of heat, 13.25 joules of heat need to be supplied to expand the piston cylinder arrangement so that the pressure reaches to 3 atmosphere. All right, next question please. Reversible. Heat engine absorbs heat energy from a stream of hot gases whose temperature falls from T1 to T2 Engine rejects heat at constant. Constant temperature sink. T naught. Assuming at any reversible cycle operating. Under these conditions, then show maximum efficiency of this engine is can be written as maximum efficiency is 1 minus T naught by T1 minus T2 into ln T1 by T2. All right, you have to show this, prove this. Pretty simple question. All right, let us discuss. So there is a reversible heat engine which absorbs heat from a stream of hot gas. Okay, so it's not a source of infinite temperature. Okay, not a thermal energy reservoir. Okay, so that its temperature is going to decrease from T1 to T2 and reject a heat at a constant temperature sink. So it's a thermal energy reservoir with T naught. Okay, whatever amount of heat you reject. Then you need to show the maximum efficiency of the engine will be like this. Okay, the expression for that is this. So let us start. So let us draw. So there is a hot gas. It is connected with a engine, heat engine, HE, and it is connected to a sink that is at T naught. Okay, so this temperature is gonna eventually decrease from T1 to T2. Okay, so heat is supplied here, that is Q1. Work is gonna extract from here, and Q2 is the heat rejected. Okay, so we know that efficiency of a idle engine is nothing but 1 minus T lower by T higher. Okay, so efficiency is 1 minus T lower by T higher. So 1 minus maximum efficiency can be T lower is T naught. T higher is something to think upon, ponder over. Okay. Also efficiency is work net by Q supplied. So Q, it can be written as Q supplied minus Q rejected by Q supplied. So what is Q supplied? It is Q1 minus Q2 by Q1. So that is 1 minus Q2 by Q1. All right. What will be Q1? Q1 will be MC into temperature change of the hot gas, MC delta T. Since Q1 is MC T1 minus T2, all right, MC T1 minus T2, all right. Now, for a reversible case, you know that entropy of the universe should be zero. Entropy of the universe should be zero. So since ds of universe for a reversible case should be zero, so let's assume that it's from the surrounding it's zero entropy, and entropy of a system is ds of 1 plus ds of 2 equal to 0. So what is ds of 1? MC ln T2 by T1. Okay, and what is ds of 2? That is q by, because it's at a constant temperature, tds is dq is equal to tds, so dq is q2 by t naught, and it is equal to 0. From here you will get the q2. So q2 is minus mc ln t2 by t1 times t naught. So I'll write like this, minus times t naught. Okay, or you can write t1 by t2 as well. Take the sign inside, t naught mc ln t1 by t2. So that's your q2. All right, put this q2 and q1 back there. So put q1 and q2 in this equation 1. Okay, so efficiency is 1 minus mc ln t1 by t2. Okay, that is q2. And what is q1? mc t1 minus t2. Okay, t1 minus t2. So if you put all the values, you will get your final expression, that is efficiency maximum. It cancels out. So maximum efficiency comes out to be the result required, that is 1 minus t naught by t1 minus t2 ln t1 by t2. Okay, that was required to. All right, so that is it for today's session. So all of these recordings are available. Those who have enrolled for the Nptel course, Thermodynamics. In the sheet, you get all the links of the recording as well as the Google Drive folder link where all the PDFs are uploaded. And those who are first time watching my video, so it's all the lecture videos are available on my YouTube channel, that is Nptel with Varnit. Okay. And in the video description, the link of the PDF Google Drive will be there. I hope you all are regular to the lecture videos and taught on the portal. And if you have missed the tutorial, please go through rigorously again. All these questions are of very good quality. So I'll see you on the next class on next Tuesday. All right. Bye-bye.